All right, let's begin. Let me start off by thanking you all for joining us today. It is my absolute pleasure to be continuing this series of webinars that ProSoft has been conducting to share some of the issues we have seen in the field and how we solve them. Today's topic is absolutely interesting. We'll be looking at safety communication over wireless networks and some of the important considerations that you need to make in the field. An outline of this webinar: I'll start off with a short introduction about myself. We'll look at just the basics of what safety is and the role of wireless in safety. We'll talk about some of the questions you need to ask yourself before embarking on this endeavor, and we'll close it off with a quick Q&A session, or as Hamish likes to call it, a quick quadra session. As I'm going along, please feel free to type any questions that you have in the meeting chat, and we'll go through them at the end of the presentation. So while we're at it, let's get introduction out of the way. My name is Simon Kembo. I'm a technical support engineer for ProSoft Technology. I've worked for ProSoft for near 5 years now in both wired and wireless solutions. There we go, introduction is done. Now we can move on to the actual substance. An overview of safety and control. When industry took off, there were no safety standards, so harm was prevalent, particularly to employees, but also employers and stakeholders. Because if someone gets injured on the job, training a replacement is expensive. Or if a ride malfunctions, the community, AKA the stakeholders, are at risk, like the tragedy that happened at Dreamworld a few years back. So safety standards were put in place to safeguard everyone, not just the employees. The most common of those today is IEC 61508, which people commonly refer to by its components. You have SIF, or Safety Instrumented Function, SIS, Safety Instrumented System, and SEAL. We are not going to be getting into the details of IEC 61508. That would turn this 30-minute webinar into a 3-hour lecture, and I'm pretty sure none of us are prepared for that right now. But I'll explain the very, very basics with some simple real-world analogies. The standard focuses mainly on two things: the likelihood of harm and the severity of harm. Red being highly likely and very harmful, green coming in as not likely and not harmful. And then you have a scaled spectrum in between the two. The chart would then be tiered, and based on where a system sits, it is assigned a safety integrity level, hence SEAL. Real world example: say you buy your 8-year-old son a box of Legos. The likelihood of you stepping on a Lego while going to the bathroom at night is high. While it's not deadly, it does hurt as hell. So I would sit it somewhere there on a likelihood severity chart. Once you know its position on the likelihood severity chart, you can now put controls in place to move it from where it is to where having Legos is safer. There's not much that you can do to reduce the severity. You can buy rubber Legos instead, but they would still need to be somewhat rigid. So you could probably move severity this way. What you can meaningfully do is reduce the likelihood. You could start instituting a JSC in your home. Every night before everyone goes to sleep, you pull out the JSC and tick off all the requirements. Have all the Legos been picked up? Tick. Have they been put in the correct location? Tick. Have they been counted and verified? Tick. Have they been recounted and re-verified? Tick. Then you sign and your partner signs and your son signs. I may have taken it a little bit overboard, but you get my point. That would move this scenario to an entirely different SEAL level. And that right there is the basics. Now you're probably wondering what role wireless has to play. So sometimes wireless systems cannot be avoided, especially when you have mobile equipment, your cranes, your trains, your elevators, etc. You're going to need a wireless system. They'll be inevitable. Let's look at another real world example. You have a train carrying goods and people on a track. When you have a train like this one, a common setup would be to have a radio at the locomotive communicating to a radio on a brake van at the back of a train. When the locomotive decides to stop, the PLC at the locomotive will send a signal to the brake van to say, engage the brakes, and the whole train comes to a complete halt. Now, what would happen if you don't have safety here? Well, you could end up with an obstacle in the road. And if there are no mechanisms or controls in place, things go boom. Let's put this scenario on our safety chart. There is very little that you can do to minimize the severity of harm. A derailed train will almost always be deadly. What you can do is reduce the likelihood of harm. How? You could install a sensor that serves a safety instrumented function, sensing the entire path ahead of a train as the train moves. If the sensor picks up an obstacle, it will send a signal to the brake van to engage the brakes, and the train comes to a complete stop with 50 meters to spare. Provided, of course, that this entire process is instantaneous, right? Let's try a simple year 10 algebra problem. If the train is traveling at 100 kilometers an hour and has a braking distance of 25 meters, how many people on the train are aged between 20 and 30? Now, if a train is traveling at 100 kilometers an hour with a braking distance of 25 meters, it will stop with 25 meters to spare. But if the link has just a 1 second latency under those conditions, then boom. So to solve this problem, communication integrity must be incorporated into a safety instrumented function. Typical example, we know we cannot afford a communication latency more than 0.9 seconds between the controller and the brake van. So at the brake van, and here's where those safety terms come into play, we can have a safety instrumented system that will execute the safety instrumented function of engaging the brakes when it loses connection to the controller for more than 0.9 seconds, thereby adding a safety integrity level to the train's operation. And this safety functionality is actually sometimes incorporated in the communication protocol. Right? You hear of items like safety IO. That is this, basically. But in order for all this to work, right? In order to have a safety communication of any protocol going back and forth between controller and IO, for example, your wireless system must be robust, or else your controller will engage the brakes every second, and at the end of the day, your so-called moving train has traveled nowhere. Even worse, you could have this on an elevator, which we have done and seen in the field. I know you're all aware of Newton's laws of motion. If the elevator is traveling upwards at X meters per second, so are the people in the lift. Third law. If the elevator all of a sudden has its brakes applied because of a poor wireless link, the elevator will come to a stop. The people, not so much. First law. So you need the system to be reliable. And we ask a couple of questions in the field to help us achieve that, to help us understand the system pertaining to throughput, interference, and reliability. While these three are not the only considerations of a wireless system, they're probably the most crucial. Let's start with throughput. When we're talking about throughput, we're talking about the actual amount of data that you can send over your link, which is fundamentally different from bandwidth, which I'll explain if I have a minute at the end of this presentation. There's some important questions that we ask when we are helping design the system. I'll explain these questions, and when I'm done, you'll have a clear picture of, oh, that's what this guy was talking about. Starting with the first two, what type of controller do you have? What is the device pole rate? Think of your wireless link like the M3 highway. and every single packet like a car on the M3. The width of the M3 is analogous to the throughput available on your link. Like the M3, it is not going to change. I mean, unless the coalition government changes, but even that's a long shot. Here's where the type of controller comes into play. Modicon is popular for its low balance pole weights. So it'll be like traffic on the M3 at 11 in the morning, no congestion, no delays, being VAR, no latency. Change your controller to a Waco controller with the same number of I/O, it's just to look more like traffic on the M3 at 4:30 p.m. Change it again to a Profinet controller and it starts to look more like traffic at 6 p.m. You have lane constraints and congestion or latency. Increase the pole weight, you're adding more cars onto the M3, so more congestion, AKA more delays and higher latency in your communication. So if you're working backwards in your design, which of course you should never do, but just indulge me. If you're working backwards in your design and throughput is a constraint, you don't want a high polling controller at high pole weights if you have a limited throughput. It just won't work. More communication devices means more cars on the M3. Right? So more congestion and more delays. And when it comes to frequency, frequency can be equated to the bandwidth and hence the throughput. This is similar to the number of lanes on our M3. 2.4 gigahertz could be a 2-lane road. It can only have so many cars and hence so much data rate. Change it to 2.4 gigahertz on MIMO, it's now a 3-lane road. Change it to 5 gigahertz, now you have a 4-lane road, and so on and so on. And that is the importance of considering your available throughput. For interference, on the other hand, we ask questions to try and get an idea of the environment. What do you have other access points? What is the operating environment like? Have you done a wireless site survey? We want to know how many access points you have installed. Radios communicate like ancient Greek politicians on the Senate floor. Everyone shouting all the time. The more radios you have, the more the signal from one will affect the other. Even though good radios, or AKA process radios, are designed to be robust to interference, it is always a good idea to reduce it where possible. Environment is also important. Some materials are able to absorb short wavelength signals, like bricks, for example, while other materials like metal will increase reflections and hence interference. That being said, the behavior in different environments will depend on the frequency being used and the antenna technology that you're using. This is something one of my colleagues will be discussing in an upcoming webinar. Site surveys are crucial in helping decide how to configure the radio you're using. You can get a clear picture of what we call channel loading, which will help you decide what frequency to use and what channel to occupy. One survey can tell you that 2.4 gigahertz is overloaded. So it wouldn't be a good idea to put a new access point on that frequency. Another can tell you which channel to use on 5 gigahertz to reduce the likelihood of interference, which is ideally an unoccupied channel. So these are the 3 major questions pertaining to interference, and they allow you to design a more rigid and robust wireless system. Finally, we look at reliability. To help us understand whether the entire communication system design is ideal, we ask questions like, can you accommodate a data packet drop? What are the site specifications? Is mobility or roaming required? Which give us a clear picture of the tolerance of the system. Let's go back to our elevator example. Firstly, we know our elevator has to be mobile, or else it will just be a no-window jail cell. Right off the bat, we will need a wireless solution that will allow our elevator to roam from one radio to another. And you want this roaming to be so fast, no data is lost. You want it to be ultra fast roaming. That way, as the elevator moves up and switches from one radio to the next, absolutely no packets are lost, maintaining your data integrity. Another thing about tolerance is data drops. Wireless systems have a multitude of variables, a multitude of stuff that will affect how the wireless system operates. So for our elevator, which we say cannot tolerate a single packet loss, we would recommend a design that utilizes parallel redundancy protocol, or PRP. And you would of course need radios that can accommodate that. With PRP, you can have traffic replicated on two independent communication paths, thereby factoring the probability of a packet loss. The PLC will accept the first good packet it gets and discard the other, thereby providing the communication system with a fallback if one link gets disrupted somehow. Let's tie everything together with a nice pink bow. And what better way of doing it than going through the questions and simulating a design process? John Doe is designing a system that must meet level 3 seal specifications. Part of the system is a wireless component connecting the controller to 30 Profinet safety encoders, as well as some CCTV cameras for security. He goes through the design process in his head. He looks at the protocol, the type of controller, and the number of devices, and that will help him decide if he needs a high throughput or not, which will inform him of what type of antenna technology to use. In this case, we need a high throughput because of all the devices that we have. So he decides he's going to have to use MIMO technology. Then he studies the environment, does a site survey, and all that will help him decide whether he wants to use 5 gigahertz or 2.4 gigahertz. Because of the congestion on 2.4 in the area, with corporate Wi-Fi all around, he decides he's going to go with 5 gigahertz for the sake of lower interference and the additional advantage of a higher throughput. He then looks at tolerance, right? With level 3 requirement, a single packet loss would not be ideal for him. So he decides to minimize the likelihood by utilizing the advantages that come with PRP. And just like that, we have basically gone through the entire design process and decided we're going to use good radios, process radios, on 5 gigahertz in channel 48 configured to operate under PRP conditions. Right. So in conclusion, we talked about the importance of safety and incorporating it into the wireless communication system. That it is crucial to have a robust wireless system if we are relying on it within our safety instrumented system. It is important to take a step back and ask yourself a couple of questions to get a clear picture of the factors that are going to affect your wireless performance, so that at the end of the day, you have a robust enough wireless system for your safety application. All right, now would be a good time for us to move on to the question and answer. if we do have any questions. So far, we don't have any, so that could be because I'm a very good presenter and everyone understood every single thing that I was saying. While we're waiting for a bit more questions to come in, let me just talk a little bit more about throughput and bandwidth. We should probably take a couple of minutes or so. So throughput and bandwidth, as I mentioned, are fundamentally different. You would have a lot of situations where you would have a specific value given to you in terms of bandwidth. But the question is that the actual amount of data that you can go through? And a typical example would be a scenario that we saw with a customer that I cannot mention at a site that I cannot specify, where they had a wireless radio and then it wasn't operating, and they called me out and they said, hey, we have this radio and we were told that this radio actually does 400 megabits per second. But what they didn't do was look at the asterisks that would say, oh, this radio actually communicates at 450 bits per second. If you're communicating under MIMO and you're using both 2.4 gigahertz and 5 gigahertz, which is something that people would ordinarily never do. Right. Whereas the actual truth of the radio was it could have 450 megabits per second, but because of the way it was set up, the way that they were communicating, the type of antennas that they were using, their throughput could only be a maximum of 54 megabits per second. So that would be a fundamental difference between your bandwidth and your throughput. Calculating your system based on a bandwidth value would not give you the same desired effect as using the actual value of data that you're going to be sending through, which is your throughput. But again, this is something that a colleague of mine is going to be discussing on in a couple of weeks when he's going through the radio setup and the basic radio and antenna technology in a different webinar. So we have a couple of questions. First question, what would you recommend if wanting to transmit through brick walls? I heard you say brick will absorb some frequencies. All right, so with frequencies, you have what we call penetration power. Right? 5 gigahertz, for example, has a much smaller a much smaller wavelength than 2.4 gigahertz. So it doesn't have that much penetrating power, which means while it can go through a single set of bricks, it won't go through a large number of, a thicker brick wall. Right? So if you have a thick wall, you want to reduce the frequency that you're using. You want to use the lowest frequency that you can to take advantage of the higher wavelength that you can get from that communication setup. So if I was communicating out of a room, my first decision would be, if I need to get out of this environment, which has thick walls, I should probably use 2.4 gigahertz over 5 gigahertz because it gives me a better penetration power. Another thing that you'd also want to look at, which my colleague is going to be discussing on a radio setup webinar, is what type of antenna do you use, right? Sometimes a directional antenna in certain situations would utilize the most of that penetration power through where you want to send your signal. All right, I hope that answers your question. Next question, are there any international standards that govern the use of wireless communication in safety applications? All right, so this question is a little bit loaded. Short answer would be yes, they are. Long answer would be, while there are standards that say your wireless communication should be like this and that, what safety standards would mostly be looking at is the entire system, right? And that wireless part becomes part of that entire system. So if the safety standard specifies that the entire system should allow you to communicate this way and do that, there won't be as much of a restriction on the wireless component of the system, but it will be necessary for your wireless components to allow the system to match that as a whole. Let me give you a typical example. Say you have, say in the elevator example that we're talking about, right? And your international standard would say this elevator should be able to report all the information of speed and distance moved and all the encoder information back to the controller within 20 milliseconds, which I think is the SIL, is level 2 SIL specification, to say it has to return all that information in 20 milliseconds. That means your wireless system, which is necessary in that kind of application, has to be able to support that 20 millisecond data reporting requirement. Right? So while they won't tell you that your wireless system should do this and that and this and that, for you to get the rest of the system to comply with the specified standard, your wireless system also has to match that specification or meet those communication requirements. All right, that was the last question.
Hello, Simon.
So, yep.
There's another question. May I know again the recommended software used for scanning the frequencies during site surveys?
All right, so site surveys become a little bit tricky. Our first recommendation will be get people who've done them before, or get guys from ProSoft to come down. Why do I say they become a little bit tricky? I've done a couple of site surveys where you have nothing, you want to use Wi-Fi, but you have nothing within the wireless range. And then the customer would install this equipment on a specific frequency like 5 gigahertz within Wi-Fi range and would keep getting problems, right? So they call us over to site and they're like, hey, we have these sort of problems. Where are these problems coming from? We did a site survey with this company from this place, and they told us that there's nothing on our Wi-Fi signal range. And then we come in with our specialized equipment, and what we find out was they had a bunch of machinery that was vibrating at a frequency that was causing a harmonic oscillation within the area that the radios were installed, right? And that was affecting the channel that the radios were on. Right? So for you to say you have to do your survey within this specific frequency range would not be ideal, right? You would have to cover an entire possible range that is probably outside the Wi-Fi signal range. And then based on all that information, you would decide what would be better for you, right? For example, we would, if we're setting up a wireless site survey for 2.4 gigahertz, we would scan the entire 2 gigahertz to 3 gigahertz range, right? Just in case there's something that is outside the 802.11 Wi-Fi standard that could possibly affect your communication. On 5 gigahertz, we'd do the same thing. We wouldn't scan just the Wi-Fi range of 5 gigahertz. We'd probably stretch from 4 gigahertz to 6 gigahertz, just to be sure that there's nothing in that range that is going to affect your wireless communication. What sort of tools will be required for scanning? There are specialist tools, that specialist equipment that you can get that does that, which is where we recommend that you actually get in touch with someone in your area or a ProSoft representative in your area so that they can arrange for you, or you can get people who are qualified to do wireless site surveys.